make the assertion in the first place.
You've never bleeding observed it, you idiot. Come on. You're asking me to explain why it doesn't do something that nobody's ever observed.
You've never observed this force that you speak of.
Now, come on, let's stay with the coconut going upwards. You made that assumption.
You don't like that explanation, do you?
No, let's go back to the original leaf falling off.
No. This is between me and Anthony at the moment. Anthony, you said you've asserted that it doesn't go up because there's a stronger force coming down. Is that what you said?
Sorry, I'm on the phone. I'll have to come back to you 1 sec.
Oh, that's a nice one.
He's not actually claiming that as a thing. He's using it as an analogy to compare to your logic. That's all he's doing. He's not actually claiming that.
Not my logic. What I observed.
What time's best for you?
Anytime after 4:30, because I'm actually in another call at the minute. So call me back after 4:30.
No, but I'll speak to you then. Okay, Sam.
Thank you. Bye bye.
Thank you. Bye bye.
Anthony, listen. Don't interrupt me. Just listen. Every one of us in the panel has observed coconuts falling downwards. It's only you that's introduced. It doesn't go upwards. And you want me to explain why it doesn't?
I'm claiming that there's a force.
Well, that's what you claim that. You claim that, but I don't need to argue with it.
I'm just doing the opposite argument to you. But isn't it silly when I make the claim that it actually wants to go up?
No, there's absolutely no argument here because none of us have observed one going up.
Yeah, but I'm saying it's only going down because its mass is too strong for it to go up.
Anthony, this is the end of the argument. Nobody's observed it going up.
So. It's the end of your argument.
Because you made a stupid argument that I'm not going to get involved in.
I claim that it wants to go up but can't because of its own mass. The issue is whether or not it desires to go up or not. And you're claiming the same about it going down. But you don't realise that the two are basically the same.
No, it's not the same. Absolutely not the same. A coconut doesn't have a desire. You personified a coconut now, haven't you?
Yeah, but it hasn't got a desire, so it can't have a desire to go down neither, can it?
You use the word desire, not me. You're saying that the coconut wants to go. You're saying to me that you're asserting that coconuts actually want to go up, but because of their weight, they go down. You cannot demonstrate that. All I can demonstrate,
and it's the same with you with your force.
No, observation, sunshine. Observation is
a force, though. I accept I can't prove the desire for the coconut wanting to go up.
Look,
but you don't accept that you can't demonstrate your coconut wanting to go down.
You have legal training. You could not go into a court of law and say, look, it wasn't observed, but we assert that it could have happened. That's absolutely fucking
You couldn't go into a court of law, make an assertion and be asked for proof, not provide any, and expect
Observation is a valid evidence for any case. Eyewitnesses observe.
And in any case,
not in and of itself.
In any case where observations are the main piece of evidence, they apply something called the Turnbull Guidelines, which gives 6 questions that the judge must ask the jury to deal with. And it always starts with, well, this guy may believe that it's true, but it doesn't make it true. His strength in his opinion might make it, he may believe it's, look them up, the Turnbull Guidelines. Just because you observe it doesn't make it true. So what you're saying is you observe this force. We're saying there's no force there, Mark. In the same way that I know there's no force that makes the coconut wanting to go up. And that's obviously ludicrous and silly. But you don't think it's silly.
Classic obfuscation.
Mark, I posted a video in the Hangout where a guy uses a car. Gravity is basically an acceleration force down. And this is an experiment I posted where a guy uses a car to simulate, gravity, but the force of the car. When you accelerate a car, it pushes you back. And so he uses his car to demonstrate how gravity. Yeah, with balloons. He uses a helium balloon and then a balloon filled with air, and it shows the differences.
Yeah.
And how gravity works and buoyancy works and all that. So yeah, it's a really good experiment there. Simple.
Yeah, well, we can only draw a conclusion from it, and I draw the same conclusion as to why things fall downwards, and that we all observe things that fall downwards. Anthony just wants to obfuscate it by giving us a story of, well, coconuts actually want to go upwards. I'm not even going to go down that road, because my point, and I put a video earlier on today, that it's a non sequitur to argue about an egg floating in a salt solution as to what shape the world is in, or what shape the Earth is. Globers need gravity to hold people to the floor in Australia. We don't believe that anyway, but there is still a force that goes downwards. What you observe is you throw something up, it comes down. even the helium balloon, and also water vapor. Eventually, it cools down, becomes a heavy globulus of water, and it falls downwards, ready to be heated up again, and it goes upwards, but it always comes downwards. It never goes beyond.
Do I have to suggest that?
Can I?
Wait, I just want to say something. This whole what goes up must come down, are we all actually confident that this is a natural law, considering that there are things that do not seem to come down?
What doesn't come down?
Stars, sun, moon. They don't seem to be going down.
Different subject. We're talking about things like egg and water and salt.
Okay, but this thing about what goes up must come down does not seem to be 100% concrete, a law of nature.
Well, we didn't see the stars go up or the sun go up, did we? What goes up must come down. That's what you and I have experienced throughout our lives.
But are we certain that that's 100% true for every single thing in reality?
Well, I'm starting with what goes up. Okay, not what's already suspended up there for some reason. What goes up comes down.
I mean, if you observe something, if you toss like a tennis ball in the air and it comes down, you do it like 1,000 times and it works every time. It doesn't mean on the 1,001st time it's going to come down, but it gives us, I mean, it does not 100%, but it's, you know, pretty.
Maybe it all,
99%.
maybe the unwritten rule is that if it's of the earth, its tendency is to go back to the earth. For example, a tennis ball, or let's say a balloon. A balloon is what? Made of petroleum. So we put here, so maybe that's actually the rule. It's of the earth, it seeks its ground, I suppose. Maybe that's the law we're missing.
This has nothing to do with the shape of the planet or the earth.
Okay, let me bring that up back. Let me bring that back up real quick, Anthony.
Yeah, I am here. Sorry, I've not been listening. I keep having to answer.
That's okay. Yeah, that's okay. I'm just going to ask you a question real quick, just a yes or no question. When you bring up this issue of gravity and this downward force, are you trying to argue for the shape of the Earth?
Not really. It has
okay, that's enough.
The shape of the Earth.
No. That's enough. That's enough. Mark, I would suggest that your video that you posted as a non sequitur is a straw man, because that's not the argument Anthony is making.
It is a straw man. I know exactly that.
Oh, what a day! What a lovely day!
Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you'd like to support this channel, there is a super chat that runs alongside each of these shows, well, while they're live, but there's also a PayPal link in the info box below the video. Most importantly though, if you'd like to join the discussion, simply mute the page you are currently watching, then click the link in the info box below this video to join the panel and express your views on the shape of the Earth. If you do join, please don't swear. If you do, you'll be ejected, and if you are, please don't try to rejoin the stream using sock accounts. You'll be warmly welcomed back on the next stream. Please also share the show. Sharing the show obviously increases the live audience, but this in turn increases the chances of a more diverse panel. So please share the show. And one last time, if you're new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Now, we are joined by P. Mars, the Plain Truth, Physics Warrior, Sleeping Warrior, Mark Doxey, Make 4, Jimbo, Eric, and Earth Flattener. Good to have you all.
Greetings, Earthlings.
Travis, will you ask those questions again for the sake of the public audience? Because
I didn't know. Right, I didn't know that we were offline. Yeah. So my question to Anthony was whether or not, when he's addressing this gravity and downward force issue, if he's addressing the shape of the Earth in his argument. And his answer, if he's not there, his answer was no. So then my analysis of your post for a non sequitur, that is, your issue is his argument for gravity has nothing to do with the shape of the Earth, and you're saying that's a non sequitur. But my point is that your point in posting is actually a straw man, because that's not the point he's addressing. So
yes, it is a straw man, and I'm just being satirical. That's all.
yeah, but the
What's
problem.
happened?
Hold on, just real quick. No, just hold on, Jimbo. I'm sorry. Hold on. The only problem with that, Mark, is kind of like when another panelist who has been on as a regular said that was a joke, but nobody knew it was a joke. The problem is, I didn't know you were being satirical.
Well, I don't really care. Let me reply to that before somebody else starts talking. This has gone on for 3 months, and it's nothing to do with the flat. Hang on. There's definitely personalities that go on in this hangout. This has nothing to do with the flat Earth. I would love this to end and get on with the real meat and potatoes of the shape of the Earth. It is about personalities. I know it is. But I was just being satirical. It's all part of the debate. It's brought it up, and I'd love to see an end to this now.
Well, it's not likely to end now or for a long, long time. What I'd like to get to is neutral buoyancy, zero force. Now, forget zero force, zero of anything. What is zero? Why is it being so mistreated? You talk about neutral buoyancy, and then you're all over the map. Now, zero as a function. 0 chickens can lay 0 eggs. 0 apple pies, by consequence, can feed 0 people dessert after a meal. You see, 0 force does not need definition. You do not have to define force, because when there's 0 of it, there's none in existence. You cannot define something that's not existence. Just as 0 chickens, you can't define a non-existent chicken. You cannot do anything with a non-existent apple pie. You can define one, but there's nothing there. 0, by its use, depends where it's used. It has context. In CNC milling, 0, 0 is not just numbers. They're where your tool head starts to create whatever and carve out whatever the machine is going to do. That's home. That's an actual physical location. It's necessary. But 0 on a timeline is your origin. In fact, if you look up the definitions and working with timelines, you'll see that 0 in the middle of all those coordinate points is not a 0 as in the number 0, nothing. It's your origin. It's the letter O standing for origin. So when we're back to neutral buoyancy and we say 0 force, and someone asks, well, define force. No, define 0, because you're defining nothing. There is no force to define. I think that's the point everyone's missing. That 0, it means there is no force. You don't have to ask someone to define it thereafter. It's non-existent.
Precisely.
I've kind of missed a lot of the last of what was just being said, because I had to go in and out of mute for work stuff. But
I was just saying that defining, someone says, okay, with neutral buoyancy, the force is 0. No one disagrees with that. But what is 0?
Actually, Rumpus disagreed with that yesterday.
Yeah, exactly. And I told him about 0 chickens. I can sell him 0 chickens. He can give me cash money, and I can give him no chickens, and I'll be happy to take his money, because I don't even have to deliver. I can deliver him air. Yeah, I can deliver him invisible goldfish.
That's why Rumpus was completely wrong yesterday.
0 is 0. If there's 0 force and neutral buoyancy, then you do not have to even define it any more than you would 0 chickens, or 0 trowels, or 0 cats, or 0 dogs. You don't invent something to quantify nothing, which is what they want to do when they say, oh, neutral buoyancy, there's 0 force, but there's forces acting all over equally and blah, 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 and up and down, and it's equalized. And no, 0 is 0. No matter how you want to break it down, in this context, 0 force means 0 force. And in nothing any way you want, you're being silly.
In addition, Rumpus likes his mathematical formula, right? If you've got a force, F equals ma, you must have an accelerating mass. But if you haven't got an accelerating mass, mathematically speaking, and that's Rumpus's favorite bit, then you don't have a force.
Yes, F equals ma comes with extra stuff called a vector direction.
So if you have two, like, let's say pickup trucks tied together and they're both accelerating in opposite directions at the same amount of force, so they're essentially not going anywhere.
Yeah, you have two pickup trucks.
Force. So there's no force being acted upon that.
Yeah, but you've got two pickup trucks, haven't you?
It's neutralized. It's canceled.
Well, that's essentially what's going on with neutral buoyancy.
Yeah, but you haven't got two pickup trucks in the form of gravity and something else, have you? You need to have the interaction.
They have sea monkeys in there that they're not showing us, like little
three-toed gnomes.
Toe sea monkeys.
Yeah, you have the force of gravity pulling it down, and then the buoyant force pushing it up at the equal rate. Just like,
but we're not defining up and down. We're saying force equals 0 in neutral buoyancy. Let's quit moving the goalposts. 0. There's no force. You don't have to define it. Makes your job easy.
Have we not gone through the fact that a force is simply a transference of energy? I thought we've gone through this a million times.
Well, mathematically, force is an accelerating mass. So if you haven't got a mass that's accelerating, you haven't got a force.
Changes in acceleration is different than motion. We call it accelerating around a circle. If you drive in a big loop, even if you maintain your speed at 60 miles an hour doing 360 degrees around a maypole, you're accelerating around your velocity and your vectors are changing because you're not going in a straight line. So you accelerate around a corner even if you maintain the same speed. So figure that one out.
If I'm standing on a scale, the force of gravity is causing weight, even though I'm not in motion, there's still a force acting upon me.
Please try to use the word mass and try not to use the word weight as much as possible. Weight changes or varies. It's a variable. Mass remains constant. You can't take a gram of gold, stuff more atoms in it, have it maintain the same volume, and increase the density.
My point was you could have a force acting upon you if you're not in motion. That's all I was saying.
Yeah, you could have, but you'd have to demonstrate that interaction.
It happens all the time. Like right now, I'm not moving, but I still have a weight caused by the force of downward acceleration.
Well, we use the word dead weight. Dead means dead. No force is acting on it.
If you're going to claim that you've got a force of gravity acting on you, but you're not moving, or even if you are moving, you've still got to show that tractor's pulling that rope, right? We can see the tractor, we can see the rope. Well, how do we see the gravity other than the own density, the mass of the object itself?
You stand on a scale.
Yeah, that's called measuring the mass.
Measuring the
Scales?
mass in its relative. Hold on,
mass
you missed a bit. Hold on, sorry, P. In its relative density. So you're measuring. If you stand on a scale, it's how much you weigh in air.
It's how much you weigh.
If I may, I have a physics question that I don't think I've done here, and maybe everyone could take a minute to think about it and give one of three answers. You have a scale. You have a large ectimer weighing 2,000 pounds exactly. When you flip it and the sand starts to fall, does the mass measured on the scale, on the indicator, read higher than 2,000 pounds? Lower than 2,000 pounds, or does it stay exactly at 2,000 pounds?
Place your bets now.
That is a trick question, I suppose.
It's counterintuitive. It's not a trick question. We can do it physically and measure it. So the answer is clear, but I'll leave it up to everyone to decide whether while the sand is falling, the scale measures a greater mass, a lesser mass, or stays the same, all during the time the sand is falling.
Let's get it with numbers. Just give us one more time with option 1, option 2, and option 3 so the chat can take part.
Okay. Your egg timer, when you flip it, it weighs 2,000 pounds before you flip it. As the sand falls and hits the bottom, and all the time the sand is falling and hitting and gathering back in the bottom of the egg timer, does the reading on the weight go up over 2,000 pounds? Does it drop below 2,000 pounds? Or does it stay exactly the same once the sand is flowing?
Got to drop below.
Yeah, I would say the same. Drop below.
Didn't give it an option. So option 1, does the weight stay the same?
But you've introduced time while it's dropping, so that's the variable, isn't it?
I don't know. That's the question was placed the way it was.
Yeah.
While the sand is falling, quite simply, over any period of time until it's done,
the bit of sand that is falling is not exerting any pressure or weight to the actual glass, so it would go down for the duration of the flow until the flow finishes, and then it will go back to the original weight, in my opinion.
There are others who agree with you that it decreases, that instead of 2,000 pounds, it'll be 1,999, say.
Oh, I agree with him, but for different reasons.
Okay. Are we ready for the actual answer?
Yes, please tell us.
Well, are you going to be able to prove your answer?
Hold on. Just before you do, hold on. Hey, Zinder, how you doing?
Hi.
Can you say a bit more than just...
Fine. Everyone okay?
Very well, good to have you.
Actually, before he reveals the answer, let's get other people's... I want to know what Nathan thinks.
I'm not voting.
Come on.
That's the safe way. That's a good route. It's brilliant. It's actually genius.
Okay, I mean, I'll give you some of the chat comments, though. So, M. Scott Veach says it will increase. A few people say it will stay the same. I'm sure, yeah. Chris Berry say the same. Who else said say the same? Goldfish Brain Al says stay the same. I think option 2 or B will stay the same. So, 4 Wind says stay the same.
There's only 3 wait. There's 3 options, right?
Yeah.
Not 4.
Yeah.
Increase, decrease, stay the same. Anybody saying increase? Doesn't look like anybody's saying increase.
Yes, M. Scott Veach said increase.
Yeah, he did.
And guess what?
And oddly, me and Mark are both saying
he is right. He is right. It increases. When you turn the sand upwards and raise it higher, it increases the potential energy that needs to be released. That is expressed as, well, weight on the scale over the 2,000 pounds while the sand is falling. It weighs more.
Yeah.
Shout out to M. Scott Veach. M. Scott Veach got it right. M. Scott
Good
Veach,
on physics. Good for him.
Yeah, but now I want to see proof that this is true. Have you got?
Yeah, I know. I told this one not knowing that I was going to tell it today, but I'll try to research it overnight or whatever. And
assertions made without evidence can be dismissed without evidence, right?
Well, I know, but well, anyway. I'll try to find the physical, concrete evidence of the scale and the weight falling or the mass falling, and it's actual fact. M. Scott Veach is right. Your weight increases during the time that the sand is falling.
And the explanation for that concisely is what?
In fact, I might be able to do it. I have a nice, precise jeweler's scale that goes into grains even. And if I can find a small up to 400 or 500, 400 gram egg timer, I could probably do that experiment live on camera. Let me see. I might check the dollar store for little egg timers today, and it should work even on a little jeweler scale.
So can I just ask what the explanation for it gaining weight was, please?
The storing of energy, raising the potential of the body that's on the scale by raising the sand to a higher elevation.
I would have said that because when the falling,
it must be released.
I would have said that because when the falling sand is in that state in between where it's not touching the sand that it was in, and it's not touching the sand it hits.
It's so counterintuitive. It goes against everything. Even me, I would think logically it should weigh. For me, logically, and it's not logical, but just thinking it should weigh less.
Yeah, because
while all that sand is in the air, it should weigh less. That's pounds of sand in the air.
It's not interacting with the sand that it's falling from, nor is it interacting with the sand it's falling to.
But the grains of sand that are hitting the bottom are creating like an impact, and that impact is being interpreted
as exerting a lot more force, equal to the potential that was stored in it.
It's an excellent question.
Because it's so counterintuitive to the way we try to assess something in physics like that. That's a lot of sand in the air. It should have zero weight on the scale while it's midair. You think that way, but in the physics, in the real world, that's not how it goes.
I've got another example that's really counterintuitive. You get a ping pong ball and you get a vacuum, but instead of having the vacuum on suck, you switch it and put it on blow. you can get the ping pong ball to float and levitate according to the strength of the blow that the vacuum's pushing, right? That makes logical, reasonable sense. We all understand that there's a force underneath by the vacuum, in contrast to the force of gravity. But anyway, what happens if, instead of having a ball, if you get like a piece of card, square piece of card, shut up, and you put the card underneath your hand, the force of the vacuum blowing on the underside of the card is holding the card to your hand. As you lower your hand and get closer and closer and closer to the source of the air coming out, you get it to a certain point and it sucks it off your hand instead of increasing the force.
Aerodynamics. That's how an aerofoil and an aircraft works, isn't it?
James, how precise is your scale that you talked about? Is he here? I think he went AFK.
Yeah, he might have.
So what I wanted to say is maybe he can measure something. So if I take like a ball of iron and put it in the water and put it on a scale, it will weigh less than if I would make it in the air, right? Because of the relative density.
Just to say, the scale I have has 5 units it can measure in, including drams and grains.
Oh, nice.
So it can weigh a gram subdivided into 157 portions. So it's very accurate. It's a jeweler scale.
Yeah. So because of relative density, things in the water would weigh less, right, than in the air, because the density of the air is less than the density in the water, right? Is it right? Or did I get it wrong? Okay. Never mind. So now you weigh these grains of sand on sea level, and then you weigh them on, like, I don't know, 3,000 feet higher. The air density, so the air pressure will be lower, so it should weigh more on a mountain, right? Or did I get it wrong?
Are we still here?
Yeah,
still here.
I can't hear anyone. So
Nobody responded.
So can you make this experiment, or not experiment? Sorry, I know people have a problem with this word.
I call them tests, or just
can we make this?
Far from an experiment, but it is what it is. Sometimes
can you make this test?
Do a bunch of tests to maybe exclude things that if you do tests before an experiment, you might not even be able to do your experiment because the tests already prove that the experiment is not worth doing.
Yeah, let's call it a test, all right? Can you make this test, like measuring the weight? Sorry that I have to use this word, but everyone else uses it too. So can you? No, the mass is something else.
No, I don't.
Can you measure the relative?
I measure the mass.
No, weight and mass is something else. So can you
That's
measure
right. That's what I'm trying to help get boneheads to get.
Let me make a point. Sorry. Can you measure the relative
mass and weight? Unless you understand that, I'm not doing this for you at all. I'm doing it for people who will actually kind of try to understand the distinction. You kind of believe that you can stuff more gold atoms into a gram of gold and increase its density. You don't understand enough to understand, even if I do this.
I do understand what is the difference between mass and weight, dude.
That's exactly what I'm saying. I measure mass. I don't measure weight.
Mass is constant. Weight is relative.
So weight is a variable. That's not relative.
It is relative.
It's a variable.
It is relative. Can we say that? Or is it wrong?
No.
No, it is not relative weight?
No.
No?
No.
Okay.
You go to the moon, you weigh 1/6 your weight on the Earth.
Jim, so it's relative.
He's agreeing with you. He's agreeing.
It is relative. Weight is relative. Mass isn't. Mass is constant. So to make my point now, I don't use the word weight anymore. I use the word relative density. All right. The relative density should be different when you measure it on sea level than when you measure it on a mountain, because there is
I'm not
less
on a mountain.
air
I am about 230 feet above sea level, so I don't think that's gonna make too much pressure difference atmospherically speaking.
Yeah, but if you go higher,
look, the scale is calibrated where you are, People don't understand stuff like that. I don't know.
It is
You
calibrated
have
where you are, yeah?
goalposts, portable, and you take them and you move them and plant them in the ground anywhere you want. You're all over the map. Like I say,
then
my scale, I know. It says it's a mass. It's an RBS mass device. It
Well,
weighs
then,
mass, not
how
weight.
much does it cost, something like that? Because it looks like I have to do this
Jeweler
by
scale.
myself.
Yeah. It's about $100 for a jeweler scale. You can get them almost anywhere. Usually they'll have at least 5 scales, and most of them, the practical ones will weigh up to 500 grams. You get this 500-gram mass that you calibrate your scale with, and that way you know it's accurate.
All right, so
you can weigh even grains, which you can subdivide 1 gram into 157 equal parts.
Yeah,
one grain is 157th of a gram.
Yeah, that's great. So I have the
totally
only thing I have to do is buy this scale. Then
And an
I'm
egg
going
timer.
to weigh an object on it that is on sea level, and when I go to the mountain, that is,
You're
let's
going to
say,
recalibrate your
3,000.
scale, aren't you? You're going to recalibrate your scale on the mountain, aren't you, eh?
Why? Why?
Why? Because you're on a mountain now.
Yeah.
Idiots. I don't know. I give up on this. Anyway, I'll try to find that
I want
timer and do a test. This is not debate. It's just babble.
I
Like
want to
said.
see the difference in the relative density. Why should I
Get working on it then. I'll see you all around. Enjoy.
Why should I? Fucking. Okay, can anyone explain to me why I should recalibrate it if I want to measure the difference in the relative density? No one?
Yeah, hang on. So just run this by me again. You want to tell me the facts.
Okay, I want to see. So, according to this explanation with density and buoyancy, when the medium around me, let's say air, is less than, let's say, less dense than the medium in water, for example, like so in air something should weigh more, or the relative density should appear to make it weigh more, because the density of the air is less than the density of the water, right?
Correct.
Okay. Now I measure the weight on sea level with a precise scale. Then I measure the same object on 3,000 to 4,000 foot high mountain and see if I can see a difference. If your explanation is right, I should observe that the object on the mountain weighs a little bit more, if I can see any difference at all.
Yeah, but you have to. How would you ensure that all other variables are kept the same? Because you'd have to try and keep the pressure the same, but by changing your altitude, you go, I'm going to change your pressure, you're going to change the temperature, you're going to change the humidity.
Yeah, that's a problem. I would have to repeat it like 1,000 times and see if the results are the same, or see if something completely different happens.
So, but you know that there's another issue, another significant issue with conductive metals to do with altitude, right? Which is directly to do with the pyramids. The higher in elevation you gain, the more voltage that's up there in the sky, potential energy up there in the sky, because you're changing your elevation. You're going to be susceptible to more electromagnetic influence as well. All these things will change the perception of what you think you're measuring, and you will perceive one thing and say that's down to that, and then, but there's so many variables that are no longer the same. So I have thought of doing this myself, but remember that voltage, the atmospheric voltage, increases with every 100 feet or so. It goes up and up and up. So if you're going to have a conductive metal up there with electricity floating around you in the form of positive ions, that's going to have a serious effect, because you're going to have a significantly different differential.
Then I'm going to use a non-conductive metal.
You would need a gauze chamber, and you would also need a not a helmet's coil, a Faraday's cage.
Yeah, exactly. So
and then if you did that, then you would at least be keeping some of it. But the problem is you can't shield out potential energy. You can only shield out energy. So how would you account for the potential energy that's up there?
How do you think that there is more potential energy? I mean,
well, I know that
if I stand on a mountain and then let it go, the potential energy is only the energy that is from my hand to the ground to the top of the mountain. right?
Yeah, but this is the problem with the gyroscopes thing that Chris Monk accepted, right? If you use a Faraday's cage and put the gyroscope in it, that only shields out the energy. It doesn't shield out the potential energy. So you've still got the potential energy up there, of which there is a lot more up there than there is down here, that's going to influence the result one way or the other. I don't know which way it'd go, but I know that it's a factor that would need to be trying to control, and you can't actually control potential energy.
Okay, that's strange, but it should then the potential energy just like make this completely different? Not a little bit different? Like there is so much potential energy up there that it would make this object way completely different, shouldn't it? Or is it just a stupid assumption from me?
I don't know is the honest answer. I just know that potential energy...
Well, hold on, let me try then, Anthony. So you're talking about things, again, based on their medium, and the first thing you disclosed was about if you change the medium to water. So how much potential energy something has is, again, dependent on the medium that it's in.
Yeah.
So if you take whatever, let's say you're weighing some ball, just so it has obvious buoyancy, and you do the same thing you describe, you go up to the top of the mountain from sea level, well, why not just do it into the sea? You drop your weight, which is the scale itself, into the pool or the sea, and it drops 2 or 3 feet to the bottom, and you find a nice level bit. And because the weight of the scale itself drops to the bottom of the water, right, there we're all set, right, to weigh the ball in the medium. Well, you put it on the water and it doesn't even go down.
Yeah.
So what does that mean? Does that mean it weighs nothing, or does that just mean in that medium it's completely buoyant? So you can't even weigh it in that medium. It's irrelevant. Your scale is suddenly useless in that medium because it's relevant to the medium.
Yeah, that's why I wanted to test it in air that has a different density, because I wanted to do the same. Look if the relation to water to air would be the same to dense air and less dense air, because what I think is that when I go up in the mountain, things weigh a little bit less, but I'm not sure, and I want to disprove for myself. I want to disprove gravity by that.
Yeah, but the issue will be with the interpretation that you apply to the results, because it could go one way or the other, and whatever way it goes, I mean, I don't know which way it goes, but whichever way it goes, how you formulate your explanation for what's going on is going to be met. Because how are you going to deal with gravity, right? If you're getting further away from the center of the Earth, aren't you going to have to adjust for being further away, like 3,000 feet further away from the epicenter?
Yeah. I don't know. I don't know how to do that, but I know that according to gravity at the same location, the object should weigh a little bit less, as you said. And this is really insignificant, but if the Earth is spinning, then when you are going a little bit more up, you are going to spin a little bit faster. That would make something weigh a little less because of the
centrifugal force, right?
Yeah, exactly. And I want to disprove that for myself, because I learned that.
So, what do you think would happen? Do you think the weight at sea level would be more or less heavy when it goes up?
Well, at sea level it would be more. The weight would be more, and if you go up, it would be less. I think that this should happen if we live on a globe.
Well, the problem, like I say, the problem you're going to have is the interpretation, because there are that many factors that influence what happens at different pressures, temperatures, and the electromagnetic effect as well. The Faraday's cage and the gauze filter and the other things that go into to do with the elevation, to do with voltages. They're all things that I don't think you're actually going to be able to quantify as well as control. But in any event, they're all good. These are all things that will influence the result, and you may get an adverse result that you can't even explain. You may go the opposite way, but what's the cause, and how would you know?
Yeah, that's going to be really difficult, and I know I would have to talk to some people who understand this topic better than myself. I would have to talk to physicists who can tell me what exactly is going up there at the electromagnetic force, other forces.
If it makes you feel any better, I've also bought a set of jeweler's scales with the intention of doing this exact thing to see what happens, because I don't know what happens, and I don't really have any prediction for it other than Maybe it should weigh less because the pressure's less, because the density is less, because the whatever. But it could also go the opposite way. Like it's not always intuitive that it's going to do one thing over the other. It could actually weigh more because as the temperature decreases and the metal increases its volume, because it's like everything gets bigger when it gets colder metal wise, or when it gets hotter. And which way around? No, it shrinks, doesn't it? So its density should increase, but who knows? There's many different things that may happen, but I've bought a set of jeweler's scales to do the exact same thing because I want to see what happens.
Yeah, this is going to be a really, really hard, I don't call it experiment, but a test. So it's going to be a really hard test to do, because I would have to repeat it like so often, like 1,000 times, to be sure if it's even going to work. And if I look at the result and they are all over the place, like completely different, I can say, all right, this test is completely bullshit. But if the results are going to be constant, I can more assume a little bit more if gravity doesn't exist or if it exists. Because
thanks to Dank for the super chat. Big shout out to you. Thank you very much indeed.
So the way for me to approve my religious belief in the globe would be to make the assumption that it isn't real, and I want to disprove it. I want to try to disprove it, and if I can't disprove it, I can assume that I'm living on a globe. This is my way of thinking about this topic.
Well, hang on. Why would you assume that you're living on a globe? That wouldn't really give you the right to assume either, right? It all depends on how. Do you agree that it all depends on how you interpret the results, whatever the results are?
Yeah, that's why I don't want to be the only one who looks at this. I want an equal number of globe earthers and I want an equal number of flat earthers to look at these results, and then I would want to talk about this and see if we can get to a conclusion or not, because I don't want, of course, I'm biased all the time about everything, and everyone here is too. So,
I'll do it with you. I'll do the same experiment or the same test to see what happens if I get the same weight and then measure it. But the question is, do you tear the scales when you get up the top, or do you not tear the scales?
Turn again, please. I didn't understand.
T-A-R-E. Do you recalibrate, reset?
I don't want to recalibrate those because I want to measure it with the same calibration as at both points.
But the problem you've then got is that the plate that sits on the scale that you put your thing on is then in a different density medium than what it was before. So the thing that you're going to put your weight on is not the same as what it was when it was at ground level.
Yeah, the problem is if I would recalibrate the scale, then I would always get the exact same measure. I would always get the exact same weight, wouldn't I?
No, because not if the gravitational constant, not if gravity is varying from going away from the Earth.
Yeah, that's a good point. Let me look further into that, but I can't answer you about this anymore.
If you tear it one way, then it causes problems. If you don't tear it the other way, then it causes other problems. So either way, you're fucked.
Yeah. Let me look further into that, please, before I go into claim something.
Not tear it, and then weigh it, and then tear it, and then weigh it again, and see is there a discrepancy between the two before you do it and then after you do it.
Yeah, I don't know about that. I didn't think that much about that, and I can't give you a solid answer about this. Sorry.
And I don't know what the right thing to do is, because me and Nathan have talked about it, and me and Nathan don't agree on most things. And this is one of the things. It's like, well, which one should you do? Don't know the answer.
Yeah. Can we pull a end line to this right now, or do you want to talk further about that? Because I would like to address another topic. That Nathan uploaded this 20-minute video about the wind turbines, and I have a question about this. If you want to talk about this, or we can go on with this topic.
Nathan.
Yeah, you go ahead. Don't stand on ceremony.
All right. So can you show me this picture again with the wind turbines, please? It would be great, because I don't really have this in mind anymore.
It was Rumpus, but I can see if I can find a picture of turbines.
I thought sometimes you show those picture randomly for example, with those wind turbines, and I had in mind that it was one of those. Okay.
Yeah, I think he's on about
okay.
Sandra's P900 Coupix ones.
Okay. So to clarify, those wind turbines disappear bottom first because of the angular size and nothing else, right? Or is it wrong?
Sorry, what was your question?
Does the bottom of these wind turbines disappear first only because of the angular size?
No, I mean, you can have something crossing the midpoint. So if, for the sake of argument, you had a bit of a swell or waves, basically, then they'd cross they'd cross the midpoint of between you and the actual target, in this case, wind farm. And therefore, you would see them obscured by the thing that was in the near foreground.
Yeah, that makes sense. But is it right that in the video you said that in general, those wind turbines, at the bottom of those wind turbines can't be seen because of the angular size?
Yeah,
in general?
Well,
yes?
Angular size and the angle of view. So, yeah, the example I gave was if you have a guy that's your mate and you're standing next to him, he takes his shoes off and you back away from him, or back away from the shoes, you eventually reach a point where those shoes are too small to see. Now, most people at this point will be able to comprehend what I'm describing. Things get too small to see. Well, that's the angular size bit, but that will only be the case based on distance and your angle of attack. So if you were to increase your angle to that item, you could bring it back that way. So what they call rising up on the ball and seeing over the curve is just actually an increase in your angle of attack.
Okay. So I have a question about that. So the objects that are bigger should disappear later than the objects that are smaller, right? This is angular size. Okay.
Well, not exactly. Not exactly. No. So
the wider.
Because that's why I used the example with the guy in his shoes.
Yeah.
So if without the shoes, just the guy, he's going to disappear based on the angle that you can see certain parts of his body at. So the bottommost part of that guy on the horizon is a small angle because it's the lowest angle that you can view. So therefore, you have an angular limitation causing the angular size to be too small. But that's not to say that the bit above his shoes, there's an increase of angle. You've got a wider view, a wider angle. Therefore, you can see the top section of him, but not his shoes.
Okay. So I have a question about that. What part of the wind turbine is bigger, the bottom or the top?
What do you mean? What part is bigger?
The wind turbines, is the bottom of the wind turbine, is it wider or is it the top that is wider?
I've no idea.
The bottom is wider. The bottom is bigger than the top of the wind turbine because they were built so they are more stable. So why can I see the top of the wind turbine that is smaller, but I can't see the bottom that is bigger?
Sorry, we're talking about the width. And we're talking about that's the horizontal angle, which won't change at all. We're talking about the angle of vertical attack.
Well, this doesn't really make sense to me because...
Well, let me explain it again. So the bottommost section of the wind turbine, based on the fact that you're looking at it out at distance on the horizon, you have the most limited angle as you work your way down the turbine. So the further down towards the bottom section, the more limited the angle becomes.
I don't understand why. Why should it be like that? Because if the same person talked about these shoes, puts the same shoes on his head instead on his feet, the shoes should still not be I should still not be able to see those shoes.
No, because you've got an increased angle to his head. So you've got a wider viewing angle to the top section than you do to the bottom. As you work your way down, that person that you're looking at, the angle is most limited at the bottom. So if you put your hand out in front of you, and you lift it up towards like 45 degrees towards the sky, well, imagine that's you with somebody standing right in front of you. Well, as you lower your hand towards their feet, you're effectively lowering the angle that you're viewing at. It's the same principle. So the further down that person you go, the more limited the angle becomes, therefore limiting the angle of resolution, the diffraction limit.
So can I say that only the angle matters, not that it's bottom or top? Because, you know, let's say the person is on eye level with me, and he puts those shoes on his head, so I can still see the shoes on his head, but I can't see on his feet because the angle is exactly the same. I look at it at a straight line. But
no,
now if I
but you
the
don't.
same
That's
another
wrong.
person
Stop.
Wait.
That's wrong.
Yeah.
You have a different angle to his head than you do to his feet.
Because
How does
it
this
is
prove
on
the
my
shape of
eye
Earth?
level. Because he is on my eye level, right?
Yeah.
Because the only thing that should matter is the angle, right? It doesn't matter if it is at bottom or at the top. So if
Yes,
so
it does
if,
matter. I've just
another
explained this
person,
twice.
Another
Why is
person
it
stands on
why
top
are you
of
saying
it.
it doesn't matter when I've just explained it twice?
Okay, let me make this example so maybe you can understand what I want to say about this, because I think I don't express myself that good enough.
Okay.
So another person stands on his shoulder. This person takes the shoes and puts it on his head. So now I would say that the angle is at the same as if the person below puts the shoes on his feet, as it is as if the person on the top puts the shoes on his head. So I shouldn't be able to see the shoes on his head, or be able to see the foot on his shoe, the shoes on his foot, but I should be able to see those shoes if the first person puts them on his head.
That's the same example you gave last time. You have a wider angle of view to his head. It's not about shoes, it's about the angle of view. If you hold a protractor out at arm's length and look down the length of the protractor at something in the near foreground, their head will be wider angle than their feet, won't it?
Let's say yes. So
not let's say yes, just yes. When you look at anything, you have a different angle to the top of it than you do to the bottom of it. Not, oh, let's say yes, just fact. Yes, you have a viewing angle to everything, always, without exception. Always.
Because he is on my eye level.
Not because of anything. Everything you look at ever has a viewing angle to it. The top and bottom have different angles.
No.
Okay, let's try a different explanation. In your field of view, right, you're standing and 5 feet away from you is a person, and 20 feet away from you is a 100-story skyscraper. Now, as you look out, you will have to tip your head higher to see the skyscraper because it has a bigger angle. Correct?
Yes.
Right. So things have angles. The tops of them are bigger angle than the bottom of them. Okay? Yes, Nathan.
No.
Everything has a viewing angle. The bottom of the angle is smaller than the top. That's why you have to That's why you have to increase your viewing angle and lift your head to see a skyscraper. It has an increased angle. So that applies even at distance. Things have a viewing angle. And at extreme distances, the viewing angle can become so small that you can't see things. At the bottom of that angle, where people wear shoes, people don't tend to wear shoes on their hat, and if they did, they would have an increased viewing angle because it's higher vertically.
Okay, let me say that. So there's a building, as you said, like 100-story building, yeah. I'm in the middle of I'm on the 5th floor, the 50th floor, so in the middle of the building, and I look at another building that has the same height. If I look at the middle of the building, I have an increased viewing angle. If I look at the top, I have a decreased viewing angle, and if I look at the bottom, I still have a decreased viewing angle. I only have an increased viewing angle if it's on my eye level.
No,
Sorry.
You always have a viewing angle to everything. What part of that don't you understand?
That it doesn't matter if it's on the top or on the bottom, because it means that the radius should only the radius matters, not if it's on the top or on the bottom.
Radius of what? The angle?
Of my angle, of the angle I can view.
Okay, so you're looking at a building. It's the same size building as yours, and you have an angle to the top and bottom of it. If you get further away, i.e. the building gets pushed back another mile, does that increase or decrease the angle?
If I get further away, it decreases.
Right.
No, it increases the viewing angle. Sorry,
It increases the viewing angle.
Yeah,
so as the building gets further away, I have to tip my head further up to see it as it gets further away, do I?
No.
So the
if
viewing
I get
angle.
further away, though, I don't
So
have
the
to tip it
viewing
up.
angle decreases.
Mhm.
Right. So the viewing angle at distance decreases, and the view to the top is going to be wider than the view to the bottom.
Celestial Pole.
What? No, what did you say? The other guy?
Celestial Pole,
Who cares?
bro.
He's just a muppet obfuscating my point.
Instead of a troll,
that you have
maybe
a
I
viewing
can
angle
throw
to
in that I
everything.
found the demonstration of the actual mass increasing while the sand is falling. I pasted in the side chat.
So Nathan, what happens when I look at the top? Why does it decrease? It decreases because I increase the distance when I look at the top of the size decreases for me. It appears to decrease because it increases the distance when I look at the top, and it decreases the distance when I look at straight forward.
Do you want to go to the beach?
What?
South Celestial Pole. Way less on a plane.
Shut up, mate 4, or I'll kick you out.
Lunar eclipse.
Shut up. So what are you saying? When you're looking out at height, yeah, then you've got a viewing angle from the 90 degrees down as well as up.
Again, please.
So you've got an increase of viewing angle from 90 degrees out to the horizon down because you are at altitude. So you have an increased of viewing angle to the bottom of whatever you're looking at.
Yeah.
So when things disappear like shoes, that can be resolved by increasing the angle of attack to the thing you're looking at. Like your example of going up to the middle of a building. Well, you're increasing your angle of attack to the thing that is small, therefore bringing it back into view. Where it was invisible, because you had too small an angle when you were at ground level, you've increased your viewing angle by going up in elevation. Simple. It's all about the viewing angle.
So, for the example of the wind turbines, do you really think it matters that much that the thing that has twice the let's say twice the size can be seen? It can't be seen, but the thing that has half the size can be seen only because of a little bit of decreasing of viewing angle.
That's correct.
It is so natural. It is so naturable that I don't really get why it should matter that much. So I'm ready going to stick to the curve explanation.
Well, while you might think it's not important, listen up. It's absolutely critical.
What are we talking about? What height?
The viewing angle. What the bloody hell do you think we're talking about?
No, what height of the wind turbines are we talking about?
Doesn't make any difference. At some point, you will have a limitation of the angle to the bottom section of those turbines. Or anything in the distance.
Yeah, I don't think we can get to an agreement about that because I think it's so natural that
doesn't matter.
Really matter.
It doesn't matter if you agree. It's a fact. We have a viewing angle to everything. And at some point in the distance, you will have too limited an angle to see anything. It's always going to be about the angle. I don't expect you to agree. I don't care. It's a fact.
Yeah. So let's okay. I understand your explanation, but I don't think it matters.
It gets smaller and smaller as it flies further and further away.
Yeah.
It physically doesn't get smaller, but visually, because of the angle, it does.
Yeah. Okay. I'm just going to say I understand your explanation, but I don't think it really matters that much that an object that has twice the size than let's say the bottom of the wind turbine has twice the size of the blades should matter that much that I can see the blades, but I can't see the bottom. So
Okay,
yeah,
no problem.
I'm just going to say, all right.
I'll explain it again for a third time. No problem at all. Let's pretend for a moment that the shoes in the example are giant shoes. Giant clown shoes that are 6 foot tall. Massive, huge shoes. And we do the exact same thing as with normal shoes. We back away from those 6 foot shoes until they disappear, which they will eventually do. Their angular size is not infinite. Eventually they will be too small to see, those 6 foot shoes, like the person stood next to them. Are you with me so far? Do you agree? Yeah. Eventually, when backing away from a pair of 6 foot shoes, their angular size will eventually become too small. They'll become 2 pixels in your camera. You'll back away a bit more. They'll become 1 pixel in the camera. You back away a bit more, and they'll become no pixels, vanishing. Yeah. Would you agree?
Yes. I agree, but
hold on.
The thing
this is a two-stage process. I just need you to agree. Eventually, we've got our clown shoes to disappear. Correct?
Yeah, they will eventually disappear.
Now those clown shoes are right next to the bottom section of the turbines.
Yeah.
Okay. So the 6 foot of shoes has disappeared, but what do you know? We have a giant wearing the shoes. He's massive, enormous giant. He puts on those shoes, and because he's so tall, increased viewing angle, we see the giant, like we see the rest of the turbines.
Yeah, okay.
Yeah, okay. So we understand that as we back away from things, it doesn't matter if they've got higher stuff attached to them, the bottom will disappear through angular limitation.
Yeah, now let's put
no. Just say yes, Nathan. Thank you for educating me. That's what I want to hear.
No, I won't say that.
Oh, do you need the example with the clown shoes again, clown?
Let me explain.
No, concede that you've been schooled.
Stop interrupting me.
No,
Nathan.
I want a concession.
You too, right?
You've agreed up until this point. Get the clown shoes to disappear by backing away from the clown shoes. 2 pixels, 1 pixels, clown shoes disappear. The 6 foot clown shoes have vanished into the distance through angular size limitation. Now, what do you know? I happen to put those clown shoes right next to the turbines. So the bottom has done the same exact thing through an angular limitation. But the top's still visible. We've still lost the bottom. So I've schooled you again. Now say thank you, Nathan.
The shoes will disappear after the legs because the shoes will be wider. Then
what legs?
The shoes will disappear and then the body will disappear. And I don't see this.
You get further and further away and eventually the whole bloody turbine disappears. But in the interim, we've just lost the height of the clown shoes, clown.
Nathan, I don't see this with the wind turbines. The wind turbines...
Yeah, we do. We see the bottom 6 foot of them missing. That's the equivalent. The bottom section's gone, but we've got an increase for angle to the top section. What aren't you getting?
That it doesn't really affect the disappearance of the different parts so much that...
I'll say it again, retard. It's absolutely critical. The angle that you see those clown shoes, those 6 foot clown shoes, dictates at what point they vanish. If you're low to the horizon, you will, at some stage, back away and see them disappear through an angular limitation. Now, those shoes are next to the turbines. Do you think because the turbines are bigger, we can suddenly see the bottom section of them? No. The angle to the bottom of the turbines is identical to the angle to the clown shoes, clown. So we lose the 6 foot clown shoes. We also lose the 6 foot section at the bottom of the turbines through an angular limitation. Am I going to have to say it a fourth time?
No, I think he bailed on you there, Nathan.
And yet it is not what I can observe with other objects when I do the same thing.
Yeah, you can. When have you
no,
done
I can't observe it at the same scale you are talking about, Nathan.
You can do it at any scale. It's down to the angle. How many bloody times? You can do this on a 12-foot table. Just limit the angle to almost nothing and you will see stuff disappear from bottom up. I've done it. Have you done it?
Yes.
And did you manage to reduce the angle to almost nothing?
I did the same thing, and I observed that the angle of the wider object, no matter if it's at the bottom or not, doesn't disappear at first if it has twice the size of the top. I have observed this, but it is not on the same scale.
What are you talking about? Twice the size? Do you mean the width?
It is so
what's this twice the size?
That it almost doesn't matter.
What's this twice the size? What twice the size? The width of the bottom, you mean?
Yeah, the width of the bottom compared to the width
Who cares?
of the top.
It's down to the vertical angle of attack, not horizontal. That won't make a smegging bit of difference.
Alright, we don't agree on that.
I don't care. I'm schooling you. I don't need your agreement. This is fact. We've got you to agree at the point where things disappear. Do I have to take it slowly? Even more slowly. As you back away from a fly, it gets too small to see. As you back away from a normal pair of shoes, they get too small to see. As you back away from a pair of clown shoes, eventually they get too small to see. The same applies to the bottom section of the turbines. It's simple. Everything.
Let's take the fly. You brought up the example with the fly, so let's take this. I back away, and then first the legs disappear, then the wings disappear, and at the end the body disappears.
Why? Oh my god.
So I think that those legs that are at the bottom don't really matter that much that they are at the bottom than the wings that are at the top, because it is so negligible that it shouldn't make the same result as with the wind turbine. So this is my statement, and you won't convince me different
right. Enough techno babble. Can you see a fly forever?
Finished.
Can you see a fly forever, or will it eventually be too small to see?
Can you repeat it, please? I didn't understand the first thing you said.
Is a fly always visible at any distance?
No, it isn't always visible at any distance.
Why would that be?
Because the angular size of the fly at some point
size? So the size of the angle that you can see it at causes it to be not visible. So the size of the angle... Say it again. So the angular size is what causes it to disappear.
Yes, it is the angular size,
then,
but
we'll move on.
Let me finish.
We'll move on then, no problem. I'm schooling you, you're not schooling me. You need to shut up, we're taking it slowly because you don't get it.
No, let me finish.
No, you're not talking. I am. You don't get it and you have told me you don't agree. Now, you don't need to agree. I'm schooling a Dumbo that doesn't understand. He uses words like angular size, but doesn't get that means the size of the angle is what's caused it to vanish. So the size of the angle on something small gets it to disappear. Well, the bottom section of the turbines is small. The
Nathan,
top
the
sections...
size is a combination
you're going to interrupt my crescendo, Dumbo, when you should be listening. No problem. Let's shut you up so the audience can hear it while Thicko talks over me. So angular size causes things to disappear. The size of the angle at the bottom of the turbines is smaller than the angle at the top. So the small angle, the angular size, is what causes it to disappear at distance. The top section has a bigger angular size than the bottom section. Okay, retard? Do I need to give you this a 5th time? Not seeking agreement, seeking concession from a retard. Do I need to give you a 5th time?
At least I'm not that stupid to think that the angular size is only to vertical line, but it is also to horizontal. It's a combination of vertical and horizontal line. You are talking like it is only the vertical line, and how can you bit that fucking retarded, Nathan?
Well,
I never talked to such
well,
a
no.
stupid
I'm
person
talking
as
about
you.
the angle of attack. So at distance, I'm not talking about moving left and right.
It's completely worthless talking
sorry,
to you. Nathan.
So you're not going to let me... worthless? You mean you've been obliterated and are thick and can't take in this information, and you want to obfuscate it? If you want to see a destruction of this guy's point that it's relevant on the horizontal, feel free to reference Ranty's videos where he changes the angle of attack and causes things to become more compressed and then disappear based on height. Vertical angle of attack, not horizontal, as Muppet Boy, who needed an explanation 4 times and then bailed. Any last points, or I'll round out?
Okay, can I, after the fact on the falling sand, increasing the weight on a scale during, or mass represented during the falling, I pasted a link in the side, and it is to a well-calibrated scale and demonstrates the increasing weight during the time the sand is falling. So that'll save people a lot of work.
Nathan, before you do round out, would you mind addressing a comment in chat?
If I have to, my kid... I've just about got my kid calm enough, but go on.
Make 4, I kicked him because he was just being a troll, but he's played the victim card in chat and he's quoting, he says, Nathan had to kick me because he can't handle South Celestial Pole, lunar eclipse, sunrise, sunset, azimuth meteorites, weighing less on a plane, Aristophanes with multiple sticks, right? I kicked him. You didn't kick him. I did, for being a Burke. Do you want to address that? Can you address any of them points that he makes that he thinks you can't address?
Yeah, no problem. So in terms of all of his celestial proofs, he's affirming the consequent. It's a formal logical fallacy. If P, then Q. Q, therefore P. If the world is a sphere, then I will observe celestial rotation in the north and south hemisphere. I observe celestial rotation, therefore the Earth is a sphere. So it's a formal logical fallacy known as affirming the consequent. As for his victim card, we were fully in discussion while he interjects with celestial sphere like a surfer retard. So yeah, he deserved to be kicked, although I didn't kick him. I was indeed tempted. And with that, I will say, first and foremost, a huge, massive, enormous thank you to all of the debating panel for making this debate possible. And, of course, a massive thank you to all of the live audience for tuning in and hopefully sharing this debate. If you hated the show, you know exactly what to do. If you liked it, maybe consider sharing it with a friend or subscribing if you've not done so already. I've been Nathan Oakley, and I will see you all in the next video.
Oh, what a day! What a lovely day!